This paper focuses on the collaboration with MediHSPA to address false alarm issues in blood leak detector sensors in LDL apheresis devices. Lipoprotein apheresis is a last resort treatment for the extracorporeal removal of blood lipid, and the devices that utilize membrane plasma separation as the initial stage are equipped with a blood leak detector (BLD) after the plasma filter as a crucial safety sensor. The BLD operates on optical absorption, but during LDL apheresis, the high lipid content in the blood can cause turbidity and less scattering, leading to false alarms. The BLD proposed by Medica is based on a microspectrometer operating within the visible range with a broadband LED emitter and a multimodal optical fiber. After literature research, feasibility tests were conducted to create clinically relevant lipemic plasma samples through the addition of soy phospholipids to the bovine plasma. 6 concentration of phospholipids and 6 blood percentage were selected with a critical threshold of 0.7%. This resulted in 36 distinct sample configurations. Measurement tests were performed, creating 4 different databases considering various features applied to both original and normalized spectra with respect to the physiological solution. In an initial studies, areas under the spectra representing the presence of blood and phospholipids were considered. These features were represented on a plane, and thresholding and a linear support vector machine were applied to distinguish samples in 3 macro areas: 0% of blood in the range of 0.5 and 0.7%, and more than 0.7%. Subsequently, a transition to a convolutional approach was made to enhance performances. Original spectra were used for 3 different classification tasks after data preprocessing. Firstly, we performed a binary classification based on critical threshold of 0.7% of blood. Then 2 distinct multiclass classifications were designed. The first based on blood percentage, the second on the combination of blood percentage and phospholipid concentration. In these cases, one autoencoding was applied to labels. Data was split into training, validation, and testing sets with a split of 70%, 10%, and 20% respectively. Performance in terms of accuracy of the 3 artificial neural network implementation showed that the best results in each classification task were achieved using the database considering the area under the blood and the lipid peaks as a characteristic features. This approach proposed an efficient solution to false BLD alarms in LDL apheresis devices. Accuracy fluctuations are attributed to the interplay between the dispersion effects of the lipid component and the blood absorption peaks. Future research will focus on collecting larger and more diverse datasets to assess more powerful convolutional models and to evaluate the BLD sensor sensitivity to the free hemoglobin rather than whole blood.